more later this week, but this coefficient b is always equal to 2 pi divided by the period of the function. Now there's a problem with me telling you this. I haven't defined the word period yet, okay?
Wait, is pi 3.14 or 180?
Pi in this case will be 3.14, but don't sweat that yet. We're going to keep it as pi in here. You won't ever... You're
never going to take this apart?
No. Never going to take it apart. But you'll put pi in your calculator as pi for this one.
Get the what?
So, okay.
Yeah, when you're graphing in you'll see what'll happen is when you're graphing in radians mode, you'll put pi in your calculator, and this will let you manipulate the graph in ways that are very useful. Okay? Because let's face it, if you want to use this to show how high and how low the tide goes, okay, most tide cycles aren't in 2 pi. They don't happen every 6.28 hours. So you're going to have to change this in some way. Okay?
Could you make pi equal something different for whatever you're trying to graph? Like if you're trying to...
I know what you're trying to say. You can make b equal to something different for what you're trying to graph. You can't make... Pi is always 3.14159, yada yada.
But I thought pi was 180.
No, it's going to be 3.14 in this case. We'll stay in radians mode, and it'll be 3.14159. I know, this is going to be confusing a bit. Promise.
Both of these being the same thing.
Okay, now period, hang on a sec. Let me get to period. Here's the confusion for this. I'm getting way ahead of myself, and I apologize. Period has 2 things you're going to have to know about it. One is, with a little bit of algebra, I can prove this is true. The period is always going to be 2 pi divided by this coefficient. This is just an algebraic rearranging of this. But by definition, period is 1 full cycle or repetition of the function in question. 1 full repetition, my mature little students. I don't want any comparisons between this and a certain bodily function. Period. Anyway. Anyhow. Okay. Swing back over this way, Janine. A sine wave, which is what this is called now, a sine wave one sine wave duplicates once around that circle. On the wave, that means it starts at 0, goes to 1, goes down to -1, and goes back up here to 0. The period of a sine wave is 2 pi. Period of a cosine wave will also be 2 pi. Period of a tangent will be different. We'll get to that.
Could you keep going like 2 pi and then have...
Oh, we can keep going forever this way. We can keep going forever this way. But that is the equivalent on this graph to going multiple times around the circle.
Okay.
So this is 1 full time around the circle for a sine. So that's 1 full period of a sine wave.
Okay.
Tangent doesn't work that simply. Tangent's a little more confusing. We'll get to that. Yes, Johannes, real quick, then I'll come back to you.
So what significance, like, in a real-life application, what significance would having the unit circle on a graph be? Like, what would that provide?
We'll get to that in a little later. The unit circle, with law of sines and law of cosines, the unit circle helps you understand how to solve real-life problems where the one angle in the triangle is bigger than 90 degrees. Obtuse triangles are useful there. But mostly the unit circle is a precursor to this. This is the more useful thing. Sine was anything that moves periodically, anything that repeats itself. A spring bouncing up and down, a pendulum swinging, the orbit of a planet. Anything that happens over and over again.
The tide?
The tides can be modeled by a sine or cosine wave. So that's where the real use for this comes in, and that's a lot of stuff. But to do that, you've got to be able to take this sine wave and bend it like putty. This would be very, I mean, as Parker pointed out, I love that he saw that right away. This can only stay between 1 and -1. This repeats every 2 pi.
Well, it's a reflection of the unit circle.
And it's a reflection of the unit circle, exactly. This is of real limited use, like to model the tides going back and forth, unless the tide happens to go up 1 foot, down 1 foot, and take exactly 6.28 hours. This is going to be pretty useless. So we need to be able to manipulate it. We need to be able to take the amplitude and make it bigger and smaller.
Maybe we should change the tides.
We had to match this. Well,
Yes.
I'll get right on changing the orbit of the moon to match this.
Did you
just
know
to make the math
it's
easier.
changing itself?
Yes.
It's moving away from us?
Yes.
So we can't even do it on this.
Can we
I know.
listen to her?
Unless
We can, but-
exponentially grow.
Oh,
shrink.
all I've got to do is put a variable in here, and I can do that. But we will probably not get to that. Anyway, what B actually winds up doing, the result of this, 2 pi over the period. What this is actually used for, and I got this analogy from another math teacher, and I liked it. When you put a number here, what you're doing is hitting a fast forward or a half speed button, like on a TiVo. Okay? If I put a large number here, this sine wave will go up and down very quickly. If I put a small number here, it will stretch out the sine wave and make these peaks and these valleys further apart.
So it's like
It's like compressing and extending a slinky or another spring. Okay, so that will be the practical effect of this number. But you're going to have to learn how to pick a number to get the exact amount of compression or extension you want. If I want a tide table, for example, most tides go in a 12-hour cycle or a 24-hour cycle, so I've got to make a sine wave that starts here and ends exactly on 12 or 24. I'll teach you how to manipulate this variable for that to happen. Okay, probably not today. Janan, follow me over this way. C is called your phase shift. Some people call that a phase shift. Stay with me, guys. Now, what this really means is a counter-intuitive shift left or right. Those of you who studied functions this way, last year when you were doing functions in Algebra 2, if you had a number inside parentheses snuggled right up to the x coordinate, to the x variable, excuse me, sort of like the like in vertex form of a parabola, it always moved the function left or right counterintuitively. If you had subtraction in here, it moved it to the right. If you had addition in here, it moved it to the left. Vertex form of a parabola was probably the first place you saw that phenomenon. Now D has one of my favorite names ever. D is the sinusoidal axis.
You suck.
The sinusoidal axis.
Sinusoidal axis?
Sounds like something's wrong with your nose, doesn't it?
Yeah, really.
This is that problem I told Megan, I'm sorry. It's not, I think I mentioned in physics one day, and I think only half of you heard it, about where certain names come from. Apparently, according to one book I read, the term for sine, maybe I did say that come in here, it comes from, it was in here, oh good, okay, good, so you didn't miss this one. Yeah, it's named after a Indian word that sounds like lagoon or lake, place where body of water collects, which is really random. So sinusoidal sounds like, that's where sinus infections come from. Water collects in cavities in your head where it shouldn't. That relates to it, but that's a symptom of it. I think boogers is the medical term, actually, yes. Who knows how to say boogers in Latin to make it sound more official? That's probably true. Okay, D is the sinusoidal axis. Now, sinusoidal axis is basically your center axis. It's the line down the middle. So what the number D works out to is a intuitive shift up or down. D is an intuitive shift up or down, and what it moves is the center line. It moves the center line. It actually physically picks up the wave and moves it up or down. This is not to be confused with A, which stretches it like silly putty. For example, if I were to, it's probably the latest person in here, Johannes. If I were to pick Johannes up and just lift him 3 feet up, that would be a shift of 3 units up, and that would be represented by a +3 at the end. But if I were to take Johannes and put him on one of those medieval torture devices called a rack, and to actually stretch him so that he were 50% taller, that would be a change to A. That would be a change in amplitude. Okay? And that would be an amplitude of 1.5. Amplitude is stretching. Sinusoidal axis is moving. Do you know the difference between growing and being lifted?
Yeah.
I mean, if one of you has a little brother or sister at home and you lift them up, are they suddenly 6 feet tall?
No.
No. If you believe they are, just drop them. Let them go. See what happens. Yes?
So, So does that mean, like, instead of it always hitting the theta axis, it'll hit like the one line if it was
Sure.
every time?
Yes.
If it was,
Wherever it would hit the theta axis, which I'll start calling the x-axis, because we're going to start talking about sine x now. I use just the theta axis to reinforce that it came from the unit circle. But now we'll start saying y equals sine x. And it'll still be angles, but we'll call it x's just to be consistent with the book. But yeah, what it'll be like wherever, if all I did here, Janan?
Yes.
Sorry, thank you. If all I did here was add a 1 to the end, then I would draw the horizontal line y equals 1, and I would move everything up 1 unit,
so
and
it'll
this
go up
sine
to
wave...
2 and down to 0?
Yep, and it would go from 0 to 2, and it would hit accordingly.
I like that one.
That's the easiest one, actually. That's the best. Okay.
It's like y equals mx plus b, it's v.
Yeah, basically. There's some fun stuff. To answer your question about how like some things slow down, speed up, like the moon, you can't like, if you want to be super, super, super accurate, the moon is actually moving away from us. You can actually do things like put a variable into amplitude so that the amplitude goes up and down with change, and you can make your sine wave get smaller or bigger over time.
Oh, like sine wave.
And you can also put a function in for the sinusoidal axis, and the sine wave will essentially follow that function. So with a little bit of work, you can make a sine wave, for example, follow a parabola.
That's pretty.
I'm glad you think so, because I'll plant this seed now. At some point during the year, I'm not sure when, since I've rearranged the order of the curriculum this year, you guys are going to have an art project. And you will have to draw a pretty picture with functions. No, not like that.
I disapprove.
Andrew Luckett's cat from 2 years ago is on the wall over there. That cat was drawn entirely with parametric, polar, and other types of
Wait, is that the best one
functions.
so far? Is that what's under?
No, I haven't posted it yet. Adina's Bugs Bunny from last year was absolutely insane. I will show that to you at the end of class if I have time. But
Remember we talked about SpongeBob?
yeah, that actually would be a fairly simple one. But her Bugs Bunny was actually the most impressive one I've seen ever. Yes?
Why is the moon moving away from us?
I'm not actually sure. I think it has to do with what's called the precession of its orbit. And I'm going to try and look that up and talk about it in physics in a couple months.
It's
It's
energy.
Can I sit it on my class? Because I want to know.
It's more like it's, pardon? Yes.
Oh my God.
Yeah. Okay. But, Janan, follow me back over here.
I'm sitting somewhere else tomorrow.
Okay, guys. Welcome to Honors Precalculus. I'm going to give you a lot of information at once. To make sure that I get everything said that I want to say, ladies and gentlemen.
Mr. Belleville.
Tripod.
Gorilla pod, man.
Jesus.
Pause.